Okay, we'll complete our lectures on linear algebra and eigenvalues and eigenvectors. So as we started talking about last time, linear algebra is mainly about solving this equation, where A is a matrix, as we talked about, and B is a vector of constant values, and we're trying to find solutions for the unknowns x, x1, x2, and so forth. For example, if we have two linear equations, if we put this in matrix form, we'll take the coefficients, 4, 1, 6, 3, to be our matrix A. And then x and y are unknowns as our vector x. And then the constant vector 3, 4 as b. Now we have it in the form ax equals b. Let's say you have two vectors. Vector x, x1, x2, and so on, up to xn, and y, y1, y2, and so on, up to y sub n. X and y, these vectors, are linearly dependent. If, and only if, you could find some alpha times x and some beta times y. So a scaled x and y, add them together, and that would equal 0, as long as alpha and beta are not equal to 0 themselves. So in other words, if you found 0, that's not very interesting. Everything times 0 is 0, and it would add up to 0. But if you could find some alpha, some constant alpha, and some constant beta that's not equal to 0, add these two vectors together, and they equal 0, that means that these vectors, x and y, are linearly dependent. Otherwise, we say that they're linearly independent. If this is not true, x and y are linearly independent. Let's do an example. If I've got 4x plus y equals 3, and I've got 6x plus 3y equals 4, these are linearly independent, meaning 4x plus 1y, this vector, is linearly independent from this vector, 6x plus 3y. So if I have the equation star and the equation star star, there's going to be a unique solution. Because they're linearly independent. If, for example, I had the equation 4x plus y and 8x plus 2y, these vectors are linearly dependent because 4x plus 1y is just 2 times, or 8x plus 2y is just 2 times 4x plus 1y. So these vectors are linearly dependent. And so I'd have no solutions because they're parallel lines. If we take those equations from the first example, if we write down these equations in matrix form, as we did at the beginning, 4, 1, 6, 3, x and y equals 3, 4. And as we had before, we got the matrix A, the unknown vector x, and the constant vector b. If we multiply both sides by A inverse times A times x equals A inverse times b. This A inverse times A is the identity matrix. And the identity matrix times x is just x. So x equals A inverse b. Now, as we saw before, computers, and the best way to solve this is Gaussian elimination, but A inverse is a nice mathematical construct. But how do we find A inverse? Well, to find A inverse, we form the augmented matrix. So we take the matrix A, 4, 1, 6, 3, and we augment it by the identity matrix, 1, 0, 0, 1. So again, here's A, and here's the identity matrix. Perform row operations and turn it into I augmented with whatever's left on the right-hand side will be A inverse. And again, we do this by row operations. We can switch rows around. We can multiply a row by a constant, which we'll do here. We'll take row 1, we'll divide by 4. So 4 times 1/4 is 1. 1 times 1/4 is a fourth. 1 times 1/4 is a fourth. 0 times anything is 0. And let's just leave row 2 alone for now. We can also add a multiple of one row to a multiple of another row. So here's row 1 again. 1, 1/4, 1/4, 0. We can add a multiple of row 1. In this case, let's multiply by -6 because we want to make this the identity matrix. So we want a 0 here. -6 times row 1 plus row 2. So -6 times 1 is -6 plus 6 is 0, which is what we want. Now we've got the first row of the first column of the identity matrix. But we've got to do the rest of the row. So -6 times 3 plus, -6 divided by 4 plus 3. So you'll have -6/4 plus 12/4 is 6/4 or 3/2. And likewise here, 0 times, or -6/4 plus 0 is -6/4 or -3/2. -6 times 0 is 0, plus 1 is 1. And then finally, let's take row 2 and multiply by 2/3. So 2/3 times 0 is 0. 2/3 times 3/2 is 1. 2/3 times -3/2 is -1. 2/3 times 1 is 2/3. So we're almost home. We've got to zero out that element there. Let's take row 1 minus 1/4 of row 2. So 1/4 of 0 is 0, 1. Minus 1/4 plus 1/4 is 0. Minus a minus is a plus. 1/4 plus 1/4 is 2/4 or 1/2. And then minus 2/12, which is minus 1/6. And then leave row 2 alone. We're done. 0, 1, minus 1, 2/3. So now we have the identity matrix on the left, and then whatever is left over here must be A inverse. So to solve our original equation, going back to the example, x equals A inverse times B. Well, if we take x to be A inverse, 1/2 minus a 1/6 minus 1 2/3 times B, which as you recall is 3, 4. We do the matrix multiplication. So this is 3/2 minus 4/6. And then minus 3 plus 8/3. So bang bang theorem, 18 plus 12 divided by 12, or 18 minus 8, which is 10, divided by 12. 10 divided by 12 is 5/6. Minus 3 times 3 is minus 9, plus 8 is minus 1/3. Is our answer. In general, for a 2 by 2 matrix, we've got A, B, C, D. We want to find A inverse. First, we create the augmented matrix. So we've got A, B, C, D, and on the right, we've got 1, 0, 0, 1. Again, this is A, and this is the identity matrix. We need to zero out C by row operations. So we'll take A times row 2 minus C times row 1. And that will be AC minus AC, and that'll zero out C. So again, we'll leave row 1 alone, A, B, 1, 0. And then we'll take A times row 2 minus C times row 1. So AC minus AC is 0. AD minus CB. And now we've got minus C, that's nothing, times 0. So A times row, C times row 1. So minus C times row 1, minus C here. Minus C times row 1, that's 0. A times row 2. Now we've got to zero out B. By row operations. We'll take this times row 1 minus this times row 2 and subtract them, and that should equal 0 there. In other words, this times row 1 minus this times row 2. I've got to do it to all of row 1. So A, which is row 1, times AD minus CB. Minus B times row 2, that's 0. So this times row 1 minus this times row 2 should be 0 here. You can check that. All of this times row 1. So AD minus CB, row 1 is just 1, minus BC. So CB and BC cancel, and we're left with AD. Zero times row 1 or times all this is 0. So minus b times a is minus ab. And then row 2, we'll just write out again, 0 ad minus bc minus c and a. All right, we're there. We just got to scale these to be 1. So again, we'll take this and scale it. So we'll take row 1 divided by all that. And then we'll take row 2 divided by all that. So that's just 1. Anything times 0 is 0. And then anything times 0 is 0. And this times this is 1. But let's see what happens to the other terms here. We got AD minus, divided by that, the A cancels, and we get D over AD minus BC. The A cancels again, we get minus B over AD minus BC. And here we get minus C over AD minus BC. And then here we get A over AD minus BC. Okay, we're done because this is the identity matrix. So what's left here has to be A inverse. So to sum up, for a 2 by 2 matrix A, B, C, D, A inverse equals 1 over this denominator, which is the same in all terms, AD minus BC. We got D minus B minus C and A, where we define this term here in the denominator as the determinant of A. The determinant of A is AD minus BC. And we can see, as long as this term doesn't blow up, if this AD minus BC doesn't go to 0, this will be invertible. And sometimes the determinant of A is